Hello and welcome to my YouTube channel, The Intersection. This is Professor Muhammad Ali. We defined the alphabet in a class the other day is a finite set of symbols. And we introduced sigma as the notation for an alphabet. A, B, all the way to Z is an alphabet. Sigma is the alphabet. But we're not going to deal from A to Z. We will be dealing with maybe something like A01. That's the alphabet 01, or the alphabet AB, or maybe at the most, if we want to do 3, something like A, B, C, and any combination of these, see, like AA, B, or A, and then B, B, or BA. So this is what we're going to be dealing with. So since this is what we're going to be using, let's then look at if we have alphabet or sigma cross sigma, and that will be equivalent to sigma to the power 2. And if we have cross another sigma here, that would be sigma 3. And if you want to like if you want to see like something like maybe a cat has 3 letters, or a dog has 3 letters. So this is like 3 string of characters in this case. So all the way to sigma to the power n. So that has n number of a set contains n of letters or characters. We also will deal with sigma to the power 0, and that's an epsilon. I think it's epsilon is EPSILON, an epsilon. This is the Greek letter epsilon. And then we will and we will see something like this in a minute. So let's say then let's say this is the language that we're dealing with, and let me clean this board. So sigma to the power 0, as I said a second ago, is an epsilon. And again, just to you remember what epsilon is. What is epsilon is? It's an empty string. Another thing that's pretty important is sigma star. Sigma star. Another way of calling it, it's called clean. I believe that's his name. It's spelled this way. Clean star. Example, the word is A, B, C, the alphabet, not the word. So the alphabet is A, B, C. Sigma star is A, B, C itself, A, B, A, B, C, A, B, A, B, C, all these combination. But what I left here is also the empty string, part of this sigma star. There is also sigma plus. The sigma plus is the sigma star minus the empty string. It will be all of these without the empty string. That's what the sigma plus. The sigma star is the union of n greater than or equal 0 to sigma power n. Let's do examples. Let's say that the alphabet is 0, 1. The language is the set word such that there are the number of ones, in this word is a prime number. So 1 is not part of the language. The empty set is not part of the language. How about 1, 0, 1, 0, 1, 1, 1? Is that part of the language? Yes, because there are 5 ones. How about 1, 0, 1, 0, 1, 1, 0, 1, 1, 0, 1, 2, 3, 4, 5, 6, one more? That's 7 ones. That also belongs to the language. If the alphabet is 0 and 1, and we're looking for the number of ones to be a prime number, then that's not, and that's not. This is yes, and this is yes. Now, what's also not? Hey, let's just, I know that you all know it now. 1, 0, 1, 1, 1, 1. That's not, because that's only 4 ones. Okay, that's not part of the language. Let's look at another example. The alphabet is again 0, 1. The language is a word such that there are twice as many zeros or as ones. We're looking for a language to satisfy this language, to be acceptable by this language, the number of zeros as many as the number of ones. So if we have 0, 0, 1, that's accepted because we have 2 zeros and 1, 1. Okay, let's say 0, 1, 0, 1, 0, 0. It's also part of the language. But 0, 1, 0, 0, 1 is not part of the language because we have two ones and three zeros. So it's gotta be 4 zeros. So this not part of the language. This is part of the language, and so is this part of the language. Let's see another example. The alphabet is 0 and 1, and the language is set forward such that the size of this alphabet is less than or equal 15. Let's see what are the language will satisfy this criteria. 0, 0 is part of the language. 0 is part of the language. 0, 1, 1 is part of the language. 1 is part of the language. As long as we are less than or equal 15, will be part of the language. And also epsilon, the empty string, is part of this language. If you get asked the size of this string of this language, you can say it is 2 to the power 0 because of the empty string, plus 2 to the power 1, that's this, or 0 by itself, also part of the language, plus 2 to the power 2, 2 to the power 3, all the way 2 to the power n. And you can make the calculations. Let's now talk about finite automata. Finite automata is a conceptual theory that assumes that you have a computer with a limited memory. And there are many examples in life. You've seen them in the soda machines, newspaper vending machines, mask machines. We see them everywhere, airports, colleges, campuses. These kind of machines, they have a limited memory. So for the finite automata state diagrams, we have some rules. One is the states always represents by a circle like that. And then the accepted states always donated with a circle, and inside that circle another circle. The starting state always has an edge like so, and the transition between the states is used with edges, arrows like that. And we can give notation to each state. The book uses, in some cases, key 1 as the starting states, and the transition state from Q1 to Q2 is the transition state. The input is the alphabet, A, B, or 1, 0. And they, again, in the final state is always donated with 2 circles. So let's see some examples in how to work a finite state problem. The alphabet 0, 1, and the language that we are interested in is a word such that where we need odd ones and here is important, odd number of zeros. So we need a language where it will accept odd number of ones and odd number of zeros. 0 by itself is not accepted because there's only one 0, but there's no ones. We need both of them. 1 by itself is not accepted because we don't have a 0 with it. All right, so 0, 1 is accepted. So 1 by itself is not accepted. 1, 0, 1, 1, 0, 1, that's 2 zeros and 4 ones and 1 more 1, so 1, 2, 3, 4, 5 odd ones, and then odd 0, that's accepted. So we have an odd number of ones. They don't have to be equal, but as long as there are odd numbers of ones and odd number of zeros in the word. So how to do this? Well, let's think about it this way. Here's my first state, This is my first state. And in here, if I, and again, we care for both. So we want both. So let's assume that in my first state that I am reading a 0. So if I read a 0, I go to this state. So I'm reading a 0, I go to this state. Now this is a 0 by itself, a single by itself, so it's not accepted state yet. So if I read another 0, I go back here. So now in this case, I would end up with even numbers of zeros on this state. So this is, in this state, I would have, let's say, E here for even zeros. Let's say that I read 1, because I need the parity. There's 1 here. I go to this state. Again, I have 1 by itself. It's not sufficient. I don't have the 0 with it, so I go back. If I read another 1, I go back here. So now I have even zeros and also even 1. So that's not accepted because I'm looking for odd number of ones and odd number of zeros. So let's assume that in this state here, I read a 1 because I've read 0. So if I read a 1, I go to this state. So in this state here, I will have always odd number of zeros. So odd for O and 0, I'm gonna make a strike like that in there. So I'll always have 1 0 because I receive a 0 and then I pass it. So I'll always have an odd number of zeros. But if I read a 1, I go to this state. Now this state also reads, if it reads another 1, it's gonna go back to this state. Now I end up with an even number, E for even number of ones, because I'll have two ones all the time. Now, let's say that I'm in this state and I read a 0. I go here. If I read another 0, I go back into here. So in this case here, I'll have an odd number of ones and even number of zeros. Let's keep the zeros in the top. Even zeros, odd ones. All right. Now let's go back to this state. If I read a 1, so that's a 1 here. Okay. So in this case, I will have, let's go to the zeros because I want to put the zeros in the top like what we did here, even odd zeros all the time. So let's read the 0. So we have a 0, and then we always have an odd because once we get the second one, we move to this state. So odd number of zeros. There's also a 0 with the strike there. Okay, odd number of zeros. Let's look at the 1. We read a 1, we have a 1. Then we read another 1, we go back to this state. So now we have odd number of ones. So we need odd number of ones and odd number of zeros. So this is our accepting 2 circles here. Can't draw 2 circles with the pencil. So this is the accepting state. Now we could have named them Q0 or Q0, Q1, S1, S2. It doesn't really, these are just like a symbols. Okay, so we can say this is the Q4, in this case, is our accepting state. So let's test it. Okay, so let me change the color of the, let's say that we want to test 0. 0, we said it's not, but the language. So we did a 0, we end up here. So 0, you end up right here. 1, with a 1, we end up here. So that's 1, we end up here. So it's not accepting state. Let's say 0, 1. So we go 0 and then 1. That's an accepting state. 1, 0, 1, 1, 0, 1, 1, 0. So we did a 1, the first one here. We go to this state. We did a 0. We did a 0. We go to this state. So that's an accepting state. We did another one which is this one here, we go to this one. We read another one, we go back here. We need a 0, we go here. So that's the third 0 here. Okay. We need a 1, we go here. We read another 1, we come back here. That's this one. We read a 0, we go back here. So that's, we tested it and it works. So we say the machine accepts this language. Let's look at another example. In this example, we assume again the alphabet, and let's change it to A, B. And the language is the set of the word such that the word contains two B's, the letter B's, and need not to be next to each other. They don't have to be BB, as long as I have two B's on the word itself. BB is accepted in the language. BA, B is accepted in the language because I have two B's. Okay, two B's, I have one B, two B's, so as long as I have two B's on it, I'm not interested in the A at all. So how do we draw the state diagram for that? Okay, so here we go. We start with the starting state. This is the starting state. And if I read an A, I'm not interested in the A. So if I read an A, I stay on the same state. If I read a B, I go to this state. If I read another A, I don't go anywhere because I'm not interested in the A. Remember, we don't care. We just need two consecutive, two B's, not consecutive, but they not next to each other. Can be B, A, B, 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 A, B. So if I read another B, now I got B and another B. So that's accepting state. Do I care about how many other B's I get? No. How many A's do I get? No. So you can do them like in two arrows like that, A and B. But really, on the way we do them, we just like draw one arrow like so, and then just put A, comma, B. So whatever next, it doesn't matter because that's final state. You can also give them symbols. The book uses, I think he uses both Q1 and a Q naught. Okay, well, let's say we use a Q naught in this case, and this is a Q1, and this is a Q2, so we can say Q2 is the final state. Now, you can draw this diagram any which way you want. You can draw them diagonal like this. You can draw them starting from right to left, whatever. But as long as you show this is your starting state, if it's coming from this way, you can do it this way if you're writing from right to left. But there is another formal way of doing it, okay? And that's what I'm going to show you now. So the formal way, it's called a transition table or transition matrix, but the concept is the same. So let me find my pencil first. Okay, so it looks like this. Here's the table, and we start with the starting state, and usually you do an arrow like that and say this is our starting state, Q0 or Q naught or S1 or whatever the letter that you use there, and then Q1 and then Q2, and some books they will show a little asterisk or something for the final state. And then the output is A, and B. And so we read it this way. If we at Q naught and we read an A, we stay at Q naught. If we are at Q naught and we read a B, we go to Q1. All right. If we are at Q1 and we read an A, we stay at Q1. Stay put. We're not interested in the A in this problem. If we're interested in A, we will deviate. We'll go to another state. Okay. Now, if we are at Q1 and we read a B, we go to Q2. If we're at the final state and we read an A, we stay in the final state. If we read a B, we stay at the final state. Now, this confuse you because we don't care for the A's. We just care for B's in our situation here. So that's how formally you create the table for the transition matrix of the transition state.